Okay, so this is the quick version of what was done in class on Wednesday, September 6th, made from my living room since I forgot to hit share when I set up the camera in class. So um, let's start here. One of the first things we looked at is we talked about the legend of Carl Gauss, who was a great mathematician and scientist. And according to the legend of Carl Gauss, his teacher told him when he was in um, elementary school, she told the class she wanted to take a break, give the class some busy work so that she could just sit down at her desk and relax. And according to the legend of Carl Gauss, so she told her students to add all the numbers 1 through 100. Okay. And what he did as an elementary school kid, he was able to get the answer in about 10 minutes. And according to the legend, his teacher was extremely dismayed and upset with him for this. But what he noticed is if you pair these numbers from beginning to end, this first sum, 100 plus 1, well, that's 101. And then 2 plus 99, well, that's 101, right? And 3 plus 98, that's 101. All right, and how many times am I going to get this sum 101? Okay, and I'm going to get this sum, I would just take this number and divide it in half. Okay, so I'm going to get that 50 times for an answer of 50/50. Okay, so with finding the sum of of consecutive whole numbers, right? When we want to find that sum, because another thing that we should have noticed, hopefully the day before when we were doing our participation, is that, let's see, let me go to the other page. The staircase problem. Okay, this should have been on the participation you finished at the end of last week. And these problems we notice, this is 6 plus 5 plus 4 plus 3 plus 2 plus 1 and so on. So then the one who's would be 20, how many blocks would that take? Well, unless you want to sit there and add all the way up to 20, right? We could say, well, if I start pairing up, and what we call this last number is we call it n. Okay, so n is the number of blocks that we would, or the number of numbers that we would end up adding. Okay, but when we look at this picture, like n is 1, so we're thinking of n in this case as which problem are we on? N plus, this is n is 3, and this is n equals 4. Okay, so if we want to make a formula, because what we would do here is we would add 20 and 1 to get 21, and then we have it 10 times. Okay, so if you're watching this video, try to pause it and make a formula. Okay, notice what always happens to n. What did we do to n on the last example when we went 1 through 100? And then how do we get what we multiply? So here we do 21 times 10. Okay, so 20 is our n, so 21 times 10, make that into a formula. So pause the video for a minute and try that. Okay, and I hope you came up with something like this, n plus 1. Okay, so we always add the first and the last. Well, if we start with 1, then it's n plus 1, and then we do n, the final number divided by 2, because that's how many pairs we get. And algebraically, this is equivalent to this formula. And so what you're supposed to do, the first activity for classwork, is you're supposed to look at what I did to this picture, okay? And we see n across the bottom, okay? This is the value of n. So what would that make? So notice what I did is I doubled, right? I took the staircase, I turned it on its side, so I doubled it. So then if the bottom is n, And I have one more here. I hope you can tell what you would label this side in terms of n. And then I doubled this over onto itself. So I don't really, once I find the area of this region, right, I only want to take half of that area because the staircase was doubled over onto itself. And so what you're supposed to do is you're supposed to find the area of the figure here in figure 4, but find the area in terms of n. And then it's not like you can really show your work. Your work is done when you look at that and say, oh, that makes sense. Okay, so that's how you know you're done, when you say, aha. Okay, but again, you're supposed to be able to see geometrically how this formula is the solution to this problem. Okay, then the next thing that we did, so back to that first paper to share this one. Okay, so we worked on these toothpick houses and we did number 2 together. Okay, so again, we're looking at a formula. We want to know the 50th house. You don't want to draw 50 houses. And then a formula for the nth. Okay, so here n is 1, n is 2. So n is which figure we're on? N is 3. And so I asked the students, well, where do you see n in every picture? Where do you see n? I mean, how is this pattern growing? And what we realize is that they're always adding an extra toothpick to the top and to the bottom. Okay, I always see n going across the top. Okay, so if I say this right here in red, that's my n. Well, the bottom's always 1 bigger than my n. Okay, so 1 bigger, I hope you saw that in the last exercise, 1 bigger would be n plus 1. Okay, and then every single time along the side, we have these 2 extras, right? We have a toothpick here and a toothpick here. So if we put this all together, we would have, and so I'm going to call this, I'm going to write it like this, because a sub n is, or I could write f of n, because we do have a function. This is sequence notation, or I could write like f of n because we're making a formula, so it's a function. N is the input, the output is the number of toothpicks. And so the number of toothpicks is always n plus 1 plus the 2 along the side. Okay, so for a total of 2n plus 3. Okay, make sure you recognize if you ever think your answer is wrong, make sure if you're looking at the answer key, make sure you see if it's algebraically equivalent. So I could write this in function notation or sequence notation, or some people just wrote the number of toothpicks equals, right? Because we're making a formula or an equation, which any equation is a function. And so, we have to say, what is it that equals the 2n plus 3? Okay, so that equals the number of toothpicks. I did one more example together with the class where this is n. So we start off with this triangle where there's 3, right? And then we have, then we go like this. We keep making triangles. So now there's 5 toothpicks. And now there is 7 toothpicks, and so on and so on. Okay, so I said to the class, how do you make a formula for the number, the number of toothpicks? This is n, so let's write T equals, T is the number of toothpicks. So how do you see n? And there's different ways to look at this. I mean, I start off with, Again, and sometimes, and it's the funny thing is I can look at it and see different things each time I look at it. So sometimes some students notice, well, like if n is 2, here's 2, and then I have the other two sides. N is 3, so here's the n, and then I have the other two sides. Now let's see if that idea works for the fourth one. 1, 2, 3, 4, right? So 1, 2, 3, 4. I do have 4 from top and the bottom, and then 2 more on each side. Okay, so the top through the bottom is always the n, and then, wait, something's wrong. What's wrong? The answer is not n. Wait a minute, I see the n there. Hang on, the answer is not, the answer is 2n plus 1. Where am I missing something? Wait a minute. I know this is the answer. Hang on, why am I not seeing it at the moment? It's funny that every time I look at this problem, I can see it in different ways. Oh, right, because this is 1n. Wait a minute. Hang on. This, there's the n. Hang on. Okay, so sort of go back and forget what I said for a minute with a 1. Ah, there we go. Now I'm seeing it more clearly. Because what I forgot to do is I forgot to count the ones in the middle. I was saying 1n plus the 2 on the end. That doesn't work. So then I can do this. Here's an n with 3. Here's an n with 3, but then I have one more. Okay, now n is 4. So let's see, can I highlight 4 triangles without overlapping? 1, 2, n is 4.